little bullseye,
All right.
and then you can either use the arrows or sweep the whole thing aside.
Okay. All right. Great. Thank you.
And apparently, it's not speaking to you anymore.
Okay. Good.
Apparently.
I can't hear myself. Okay. So let's start by going over the motivation and objectives of this study. So basically, light from a variety of sources is incident in on the lunar surface. Oh. So I got a funny message on the screen here. Tim. All right. Okay. All right. Well, I guess I can keep on talking. Okay. So there are various light sources entering permanently shadowed regions near the poles that are never directly exposed to sunlight. And so the question is, could any of these be important for any reason? And so we survey all these light sources that cover a broad range of wavelengths from infrared to far UV. And so that kind of covers where most of the energy would be entering into the PSR. And so this has implications, obviously, for surface temperature of the lunar regolith, the stability of volatiles and surface chemistry, so that's probably for wavelengths more in the UV end. And also for the suitability of the moon as a platform for making astronomical observations. So people have talked about putting telescopes in PSRs to sort of do deep field astronomy. But there's also a bunch of other things you'd see as well. So that could be pretty interesting. But in this talk, I'm going to mostly concentrate on the surface temperature of the regolith. Okay, so here are a list of the sources of illumination into a PSR. So first off, there's sunlight scattered from directly illuminated surface, so that's probably the dominant one most of the time. Then you have earthshine, both direct and scattered. Then you get sort of a diffuse broadband galactic background. Then you have Lyman alpha from interplanetary hydrogen, and so that's basically what the lamp instrument uses to sort of see in the dark on the moon. Then you have zodiacal light, which is sunlight scattered from inner zodiacal dust, inner solar system dust. And then local to the moon, you have emission lines from exospheric species. So the two brightest ones are sodium and potassium. And then another possible source is sunlight scattered from exospheric dust. Now, there could be a natural source of this exospheric dust, but also you can get exospheric dust generated by impacts, such as something like L-Frost hitting the moon, or kicked up from exploration or ISIU activities. So there's or landings, or whatever. So there's a way you can get exospheric dust into the lunar environment. Oh, okay. That was supposed to be animated, but never mind. So this is just a brief overview of surface scattered sunlight into PSR. So people have kind of looked at this pretty well already, so we don't go into it too much. So there's the results from Page et al. 2010, and so they had a direct and scattered sunlight as well as direct earthshine in their thermal models. And this actually did a really remarkable job of matching the LRO Divine observations, although there were a few discrepancies here and there, but overall did pretty well. And they, in their model, assumed an internal heat flow of 16 milliwatts per meter squared, which is based on Apollo data. So then we also looked at the Mazarico study from 2011, and they estimated scattered sunlight at selected points around the poles, and they found the instantaneously fluxes ranged from sort of 0 to 7,000 milliwatts per meter squared, and annual averages range from sort of 10 to 1,500 milliwatts per meter squared. So it's conceivable that some regions, don't see any scattered sunlight at all, so they can get very, very cold. So this is our geometry that we assume. So we kind of take an idealized Shackleton crater. And stick it at a pole, and then we take each of these sources and we kind of rotate them and sort of and then sort of add up over wavelength and angle to sort of get the sort of total irradiance falling at the center of the crater. That's kind of what we do there. And this is a simple crater, simple lunar crater form. So it's a fairly good test case. So first up we have the galactic background radiance, and you see the bright band, red band running across the the image there is basically the center of our galaxy. And over the period of a year, that would sort of rotate around the crater as the Earth moved around the sun. And this is kind of based on data from sort of Helios 1 and 2 and Pioneer 10 from Linux. And so you're getting sort of fluxes there of like 10 to the minus 10 watts per centimeter squared per steradian. So next up, we've got other interplanetary sources. So we've got Lyman Alpha on the left. And again, that would kind of tend to rotate in the sky over the period of a year. And that's sort of the same sort of brightnesses as the galactic background. Then on the right-hand side, you've got zodiacal light. Now, I should have mentioned in all these plots, the sun is always on the left-hand side. And so pretty much over the period of a year, the zodiacal light entering the crater would pretty much look the same because, you know, in that coordinate system. And so for zodiacal light, we got data from Helios 1 and got color from rocket photometry. And both of those tend to be the same brightness as the galactic background. And so here is sort of a local source. This is the radiances from sodium and potassium. So on the left-hand side, we've got sort of a nominal model where you have photostimulated absorption dominating the generation of sodium and potassium. And on the right-hand side, we've got an enhanced case where you can get extra sort of sodium and potassium ejected from impact vaporization. And this kind of covers a range of values. In fact, actually, this is the right-hand side is probably not the most extreme case, so it could get even brighter than that, but it's still a fairly dim source. Again, sort of the 10 to the minus 10 watts per centimeter squared per steradian. So now moving on to exospheric dust. So in the model, we use a me-scattering simulation code for this. We assume a simple sort of 1D model for the dust distribution with a sort of surface concentration and a scale height. We use the source solar radiance model, and we use dust optical constants from Shakuratov et al. 1999, and we account for crater wall shadowing. Okay, so there has been some evidence for exospheric dust, submicron exospheric dust being present in the lunar environment from the Apollo era. People have tried since then to sort of look for it, and so on the left-hand side, there are some upper limits derived from LAMP and Clementine. This is the star tracker on board Clementine tried to look for this sort of horizon glow. And so based on that upper limit, this is the sort of light scattering that you'd get into the PSR if that sort of exospheric dust cloud was present. And then on the right-hand side, we show the Apollo 15 case. So during Apollo 15, they took a series of coronal photographs where they saw this excess brightness, which it has been argued could have been due to dust. And so if that sort of temporary, sort of transient exospheric dust was present at the pole, that's the sort of brightness we'd get. So as you can see, so for the upper limit, you've got 10 to the minus 10, again, watts per centimeter squared per steradian. But for the Apollo 15 brighter case, you can get up to sort of 10 to the minus 7, so quite a bit brighter. So another interesting case would be what would you get for a lunar landing? And so Morris et al. Have sort of simulated the dust that gets kicked up by the Apollo landing. So they actually had some data they could compare against. And so in the far field, sort of far from the spacecraft, they show some simulation results, and there you see there on the left-hand side some predictions for grains with a diameter of 800 nanometers. And you can see this sort of cloud sort of is pretty large, sort of, scales of like tens, hundreds of kilometers. And so for our crater, this is a pretty kind of uniform background cloud that we can sort of put in as a test case. So on the right-hand side, so this was kind of landing very, just outside the crater. The sunlight scattered into the crater wouldn't be very much at all, so 10 to the minus 11 watts per centimeter squared per steradian. So not a huge perturbation. Okay, so this is a summary of all the different irradiance sources I've been talking about. So sort of working from the left-hand side, we've got indirect sunlight, again, the brightest, indirect earthshine, pretty bright too. And then you've got internal heat flow, which is in red there. And then in green, we've got the various sort of weak sources I described, so diffuse galactic background, Lyman alpha, zodiacal light, and emission lines from the exosphere. And then in purple, I've just kind of added all those green ones up together because they're kind of all weak and it's easy to add them up. And then in gray, I've got the various so exospheric dust sources. So there's the LAMP upper limit, the bright Apollo 15 case, then the Apollo landing, and I might also mention that that's probably very much a lower limit. So if anything, the amount of dust thrown up by that landing would be more than that than we've modeled here. So I've just added an arrow there to indicate that. And we did, although not shown here, we did also try and simulate the brightness from an L-cross impact. Okay. So then if you take those irradiances and use them to estimate an equilibrium temperature, this is what you get. So these are temperatures kind of ranging from 10 to 70 Kelvin. And so on the left-hand side, if you just assume internal heat flow, that's in red there, that's the result you get. But then if you add the weak irradiances to that heat flow, you get that result in purple, which pretty much is almost indistinguishable. So those weak sources don't have a huge effect thermally, which is not too surprising. Then if you add in indirect Earthshine onto those two sources, you get a slight brightening, so maybe a Kelvin difference or so. And again, with the exospheric dust upper limit from LAMP, when you fold that into the internal heat flow and weak irradiances, again, you don't get a huge difference. With exospheric dust from the estimate based on Apollo 15 observations, you get a slight warming there, and maybe sort of 2 to 3 Kelvin. So that's kind of noticeable, but still pretty minor. Again, the Apollo landing, not a huge perturbation, and again the L-cross impact, not too huge. But then if you take the indirect sunlight case, again that obviously makes a huge difference. But then if you add the Apollo 15 case to that, you still get a noticeable shift of like 2 or 3 degrees, sorry, Kelvin. So in the very coldest PSRs, that sort of dust environment could could make a small perturbation, but nothing huge. Okay, so then to summarize, as anticipated, these weak irradiance sources so all add up to about 10 to the minus 5 watts per meter squared, and so when it comes to thermal balance, they can pretty much be neglected as they have been. But in the absence of surface scattered sunlight, an Apollo 15-like dust population would warm the coldest PSRs by 2 to 3 Kelvin. And you kind of notice in that last plot that you can see the influence of the T to the 4th dependence from Stefan Boltzmann's law. You can see basically, so the higher the temperatures, the less of an influence these weaker sources have. And so interestingly, an Apollo lunar module landing, the estimate we showed was probably on the low side, but it does indicate that you can have kind of nearby exploration activity near a PSR and not disturb it thermally. So you can kind of, have a few sort of small, moderate-sized missions and probably get away without, disturbing the thing you've gone to look at. But basically, the bottom line is, thermally speaking, is that all of these extra sources of brightness are unlikely to have any significant effect on the thermal stability of water ice that's either at the surface or buried. So, the water ice is going to be pretty safe. Okay, done.
Got it turned back on. All right, thank you very much, Tim. All right, we have time for a couple of questions. We have a question back here. Wait for the microphone, please, because there are people remotely.
Oh, testing. For all you remote people, I'm Larry Taylor, University of Tennessee. Tim, I'd like to ask you a question which isn't exactly along the lines of what you've been talking about, but do you still believe that there's lightning possible at the terminator due to any kind of lunar dust?
Well, I think right now with the exospheric dust question, the Apollo, we've kind of looked again with LRO LAMP and with Clementine, we're looking again with LADDI, and the exospheric dust doesn't seem to be there in the same abundances as we derived from Apollo 15 from those observations. And so if the Apollo 15 observations were due to dust, then it seems that it's very much a transient or localized phenomenon. It's not something that occurs all the time everywhere. But we just threw it in there just as a test case to see